So before moving forward, I want to make a stability analysis of the integration algorithms that we discussed. So the stability analysis for integration algorithms means that if you use a larger delta t, do you still get a result, or do you get some divergence? Okay, the result, I'm not talking about the accuracy of the results, I'm talking about whether we can get a result or not. Okay, so the analysis is called, such an analysis is called the stability analysis, and I will do it for the explicit Newmark integration method. So you can apply this approach to all the integration algorithms. Now let's do it for the explicit Newmark. So for this purpose, I'm just writing the equation of motion for an undamped single degree of freedom system. And I said I'm using the explicit Newmark for it, so u double that n plus 1 multiplied by m is equal to the forcing function fn plus 1 minus k times un minus k times u dot n multiplied by delta t minus 1 over 2 k times u double dot n delta t squared. Okay, now recall that the natural frequency omega n is equal to square root of k over m. So I can say that omega n squared is equal to k over m. And I can rewrite the equation of motion as follows. U double dot n plus 1 will be then equal to fn plus 1 divided by m minus omega n squared multiplied by un minus omega n squared u dot n delta t and minus 1 over 2 omega n squared u double dot n delta t squared. So here I'll let omega n multiplied by delta t is equal to omega. So my equation of motion becomes the acceleration at n plus 1 is equal to fn plus 1 divided by m minus omega squared divided by delta t squared un minus omega squared divided by delta t multiplied by u dot n minus 1 over 2 omega n squared u double dot n. So let's call this equation as equation 1. And also recall that in the explicit Newmark algorithm, the displacement, so the velocity at n plus 1 is equal to u dot n plus 1 over 2 u double dot n delta t plus 1 over 2 u double dot n plus 1 delta t. So let's call this one equation star. Now I will insert equation 1 into equation star. I'll get the following. U dot n plus 1 is equal to u dot n plus 1 over 2 u double dot n delta t plus 1 over 2 n fn plus 1 delta t minus omega squared over 2 delta t multiplied by un minus omega squared divided by 2 u dot n minus 1 over 4 omega squared u double dot n delta t. So rearranging the terms, I'll have the following: delta t u dot n plus 1 is equal to minus omega squared over 2 un plus 1 minus omega squared over 2 u dot n delta t plus 1 over 2 minus 1 over 4 omega squared u double dot n delta t squared plus fn plus 1 over 2m delta t squared. So let this be our second equation. Now the first equation relates the acceleration with the variables at the current time step, and the second equation also relates the velocities with the parameters defined at the current time step. Now also recall that for the explicit Newmark integration, un plus 1 is equal to un plus u dot n delta t plus 1 over 2 u double dot n times delta t squared. So this is our third equation, and at each equation we get a relationship for the displacement, velocity, and the acceleration. Now if I write these three equations in matrix form, so we are saying that writing equations 1, 2, and 3 in matrix form we obtain the following. So here I have un plus 1 delta t u dot n plus 1 delta t squared u double dot n plus 1. That's equal to, we have 1 here, 1 over 2 minus omega squared over 2, 1 minus omega squared over 2, and 1 over 2 minus omega squared over 4. Here lambda squared minus lambda squared and minus lambda squared over 2. And I got un here delta t times u dot n delta t squared multiplied by u double dot n plus I have 0 here, delta t squared over 2m delta t squared over m here multiplied by the force Fn plus 1. Okay, so I will call this vector as my quantities at n plus 1. So this is my coefficient vector, let's call it A. So these are again the displacement, velocity and acceleration parameters at the nth time step. And let's call this forcing function as our L vector. So this equation becomes equal to the following. xn plus 1 is equal to the coefficient matrix multiplied by xn plus L multiplied by fn plus 1. Let me correct this. So yes. And with this approach, I just rewrite the explicit integration equations in my matrix form, and this is the case for the forced vibration response. Okay. Now, for a free vibration, this above equation becomes equal to the following. So xn plus 1 is equal to a times xn, right? So let's start with some initial conditions. Okay, so a free vibrating system with some initial conditions that's equal to x0. Okay, so my parameters at the first time step will be equal to a times x0, right? So let's continue. For the second time step, I can write the following: a times x1, or I can just say a times x0. Now if I continue, the third time step will be a times x2, and this should give me a to the power 3 times x0. So I see a pattern here. So if I continue, at the end of the day, I should have the following: xk, the kth value at, or the values at kth time step should be equal to a to the power k multiplied by x0. Okay, so let's call this one equation star. And also remember that the response that we expect for a free vibration problem we already solved it, but let's revise it. It's something like this. No damping, so it should continue to vibrate as follows as t goes to infinity. So basically we can say that when t goes to infinity, we should still have the following equality. It doesn't change. xk must be equal to a to the power k x0. In other words, as I continue to take the power of this matrix A, this term should not diverge to infinity. In other words, when I say t goes to infinity, I'm saying that k also goes to infinity. So the power of this matrix should not diverge to infinity. So how can I express this requirement as an equation? So this condition is possible if and only if limit of k goes to infinity, a to the power k must be equal to 0. Now the question here is, how can I calculate the power of a, the kth power of a, and how can I make sure that it's equal to 0? So the answer is, I should look at the eigenvalues of this matrix, right? Meaning that, in other words, I should diagonalize this matrix. So when I diagonalize it, I will only have the terms at the diagonals. So taking the power of that matrix is equivalent to taking the power of the diagonals. So I should be looking at the eigenvalues of the A matrix. If the eigenvalues of this A matrix is smaller than 0, then I can satisfy this condition. If they are larger than 0, it means that as k goes to infinity, this A matrix will diverge. So that's why I should be checking the eigenvalues of the system. So again, let's write this in terms of mathematical equations. So let V and lambda be the eigenvector and eigenvalue pair. In that case, I can write the eigenvalue problem as follows. Ak multiplied V is equal to lambda k V. So 0 will be equal to limit k goes to infinity, a to the power k V, and we know that V is non-zero. So I can just say limit k goes to infinity, ak times V is equal to limit k goes to infinity, and instead of ak times V, I can just write eigenvalue to the power k multiplied with the eigenvectors. Since eigenvectors are non-zero, I can rewrite the following as follows. V limit k goes to infinity, lambda to the power k. And since we have the requirement that the limit lambda k should be equal to 0, says that limit k goes to infinity, lambda to the power k should be equal to 0. This implies that, as we discussed, the magnitude of the eigenvalues should be smaller than 1. Otherwise, their power will go to infinity. So again, instead of saying this as follows, we will write the mathematical term. Therefore, the spectral radius of matrix A must be smaller than 1. So this is the spectral radius . Okay, where the definition of the spectral radius is as follows. The maximum of the eigenvalues that we have where lambda 1 till lambda s are the eigenvalues of matrix A, okay? Now, when we look at this A matrix, let's come back to our problem. Now, our A matrix is as follows. So what we need to do is to calculate the eigenvalues of this matrix A and try to figure out the requirement that makes the eigenvalues of this matrix smaller than 1. Otherwise, we will not get any answer in our explicit integration. So let's do that. So say thus. So let's define our eigenvalue problem. A minus lambda I is equal to, I'm checking the determinant of it. I have 1 minus lambda here, 1 over 2, minus omega square over 2, 1 minus omega square over 2 minus lambda, 1 over 2 minus omega squared over 4, minus omega squared minus omega squared minus omega squared over 2 minus lambda. And this should be equal to 0. So when you calculate the characteristic equation for this eigenvalue problem, this is what we get. So the characteristic equation so determinant of, well, let me just write it this way. So 0 is equal to minus lambda plus 2 minus lambda squared, omega squared, lambda squared minus lambda cubed. So the roots of this equation, that's a cubic polynomial, the roots are 1 minus omega squared over 2 plus 1 over 2 omega to the power 4 minus 4 times omega squared. So that's our first eigenvalue. The second eigenvalue, 1 minus omega squared over 2 plus, not plus, minus 1 over 2 square root omega to the power 4 minus 4 times omega squared. That's our second eigenvalue. And the third eigenvalue is equal to 0. Okay? Now the critical eigenvalue here is this one. Okay? So the absolute value of this second eigenvalue will be always larger than this one. So the condition for convergence we can say that the magnitude, the absolute value of lambda 2 should be smaller than 1. So minus 1 smaller than lambda 2 smaller than 1. I got minus 1 smaller than the equation 1 minus omega squared over 2 minus 1 over 2 omega to the power 4 omega squared smaller than 1. And if you continue this operation, this is what we get at the end of the day. 0 should be smaller than omega and it should be smaller than 2. In other words, the condition for the divergence, so for the convergence, or the condition for having the spectral radius of matrix A smaller than 1 is as follows. Omega multiplied by delta t should be smaller than 1, or I can rewrite it as follows. Delta t should be smaller than 2 over omega. Okay, so that's the stability condition for explicit integration. So what we learned here is this: the explicit integration is conditionally stable, and the condition is as follows. If you choose your delta t larger than 2 over omega, omega being the largest natural frequency of your structure, okay? If you choose that delta t to be larger than 2 divided by the omega, then you will not get a convergence. Your results will go to infinity. That's the main problem with the explicit algorithms. They are conditionally stable, and if you are solving a large structure, for example, with many degrees of freedom, what governs the delta t will be the largest natural frequency. Now, in implicit algorithms, if you repeat that procedure, you will see that all the roots are smaller than 1. Okay? And this means that it's unconditionally stable. It doesn't matter what delta t you will choose, you will always get a solution. Will it be an accurate solution? That's a different question, but it will give you a solution. Explicit algorithms will diverge to infinity if your delta t is larger than 2 over the largest eigenvalue of your structure. That's the main deficiency of the explicit algorithms. So let's write it down. We said that explicit integration algorithms are conditionally stable. The time interval or the time step should be smaller than a certain value. Otherwise, the solution diverges. On the other hand, implicit algorithms are unconditionally stable. They always produce results with any time step. So the advantage of the explicit algorithms is in the nonlinear problems. You don't have to do iterations because the left hand side of the equation doesn't have any stiffness matrix. So I don't have stiffness matrix on the left hand side. I'm always multiplying the stiffness matrix with the variables that I know. Okay, so that's the main advantage. It doesn't require the iteration. You at the current step you know everything, and by using the parameters at the current time step you calculate the parameters at the next time step. So that doesn't require any iteration. On the other hand, it is conditionally stable. Yes, you don't need iterations, but sometimes this delta t could be so small that doesn't give you results at a logical time. And this is usually the case when when you want to solve a very large structure. Some of the eigen natural frequencies, even you don't excite them, may cause divergence in your solution.